Before any drainage project begins, one crucial question must be answered. What is the critical design storm? Because if we get it wrong, we risk under-designing our drainage systems, which means failures that can endanger lives and properties. To find this storm, engineers rely on hydrological model like RORB. But here's the catch. Identifying that duration, the one that produces the worst-case peak flow, can be painfully slow and manual. In this video, I will walk you step by step through setting up a RORB model for a hypothetical catchment, and then show you two smarter ways to automate the process of finding critical design storm. That includes Excel formulas and Python code. With these tools, you will save time, reduce errors, and focus on what really matters: better design decisions. Stay with me. First, let's define what we mean by critical design storm. Imagine we are designing a drainage asset for a one-person AEP rainfall event. The critical storm is the rainfall duration that produces the highest runoff peak. Since multiple temporal patterns are considered, we select the duration that yields the largest median peak flow across those patterns for that specific duration. Our study catchment is a hypothetical basin located in southeast Melbourne. It covers an area of approximately 4 square kilometers, extending 3.5 kilometers from north to south, where the outlet is situated. The catchment has a uniform slope of 0.4%, gently descending toward the outlet. Representing a low-density residential area, the catchment has a uniform fraction impervious of 0.2. The catchment is implemented in RORB with 6 sub-area nodes and 4 joint nodes which are connected by 9 reaches. All the reaches are assumed to be of type 2, excavated but unlined. In this tutorial, we focus on finding the critical design storm at the catchment outlet. The initial and continuing losses for the site are 10 mm and 1.5 mm per hour respectively. To start with, I open RORB, which I have already done. I go to the file, open catchment file. I select my catg file, which is this one, and it will open it up for me. This is basically the text base of the model, but I don't need it. I close it. I choose separate catchment and generated design storm. And then I also tick this one because I want to get my outputs in both text and CSV format. Click on OK. On this page, I need to select the important input files to the model, which are coming from AR&R Data Hub. The first thing that I'm going to select is actually the ARF, or area reduction factor values, which is a text file. I choose it. After that, I'm going to browse for the temporal patterns for the rainfall. So for that one, I'm going to select the increment file. When you go to the Data Hub, basically you download 2 CSV files. One shows the all stats, if you are interested to know what are the background actual events behind each temporal pattern. But the one that we use in modeling is the increment file, which is all those percentages of weights that we are going to use as temporal pattern. So I just choose that one. And finally, I need to have my IFD, which is coming from BOM website, but of course the link is provided in the same place when you go to the AR&R Data Hub for your designated site. After choosing that, I go to select the type of simulation that I want to have. I go for ensemble simulation, and I select a wide range of 63.2% all the way to 1%. And for the duration, I choose 10 minutes all the way to 168 hours, which is the maximum length of duration that we can have. The reason that I skipped the smaller values, because by the catchment size that we have, events smaller than 10 minutes are not really useful. And also there is no temporal pattern available for such events. That's why I start with 10 minutes. After that, by right, we need to go for filtering the embedded bursts and also choosing whether we want to have the pre-burst or not. Although it is recommended by the AR&R guidelines, I'm going to skip it in this tutorial. The reason is that it needs a bit of discussion, which is beyond the scope of this tutorial. But anyway, if you choose that, you will get slightly lower values for flows by right. And it's not expected to affect the overall process of selecting critical design a storm. So I would say that at the moment it's okay if we escape it. After that, I also need to decide about the location that the outputs are going to be stored. So I browse, I go to the folder that I've provided. So I browse output critical storm. That's the name that I've chosen for my folder. As the output folder, I select it and then click on OK. So the last window that we are going to fill is taking the parameters of the routing, KC and M, and also the loss values, initial loss and continuing loss. So I start with the KC, similar to what we did in the sensitivity analysis in our previous video. I'm going to adopt the Victoria Pierce et al. Model, which gives me 3.02. Since the site is in Victoria, I'm going to adopt this method of estimating KC. Click OK on that, and then 0.8 is the recommended value for M. I leave it as it is. And then after that, I change my IL to 10 mm and the continuing loss 1.5 as it is decided for this specific tutorial. I click on text. It will take a couple of minutes to run. Okay, once done, this is the batch file which has a summary of all results. So what we are interested in basically are these rows of information that provides duration, AEP, the temporal pattern, the rainfall and area reduction factors, and finally the peak value at the outlet of the catchment. So it's a very long table of the values. Generally what we do, we need to copy this part of the model, this part of the outputs all the way down, and then paste it in an Excel file in order to start the analysis. So the values that I need from that batch file that we got from the RORB are only 4 set of data: duration, annual exceedance probability or AEP, temporal pattern, and the flows. As you can see, for every duration and AEP case, I have 10 temporal patterns, as you can see. So if I scroll down, you can see that for every single scenario of duration and AEP, I will get like 10 values. At first, of course, the numbers look similar, but gradually when you go for the longer duration, you see the impact of temporal patterns. They get more diverse. So let's have a look on one of the cases. Let's say this one, the 2 hour 63.2%. So these are the 10 flow values out of the 10 temporal patterns. The procedure to find the maximum flow for that specific duration and AEP is that I need to copy these values, for example, paste it here, and then after that I do the sorting from the largest to the smallest value. And then following the ARNR guideline, by right I should choose the median value. Since I have 10 numbers, the median falls between the 5th and the 6th value. But to be conservative, you can go for the 5th one, and that will help us that later if we want to have a look at the hydrograph, we can literally go and choose that specific case. So this is the 5th largest value, and if I want to know which temporal pattern has given that to me, I can find it out of the 10. It's this one. That means that it is temporal pattern number 4. So I should give a color. For example, this is the value that I have got. And here, by right, I need to repeat the same process for all the durations out of 63.2% AEP, find all the 5th positions, and then see which one is the maximum. And that will be the critical design duration for 63.2% AEP. So if you really want to do it manually, I would suggest to do a bit of visual investigation first in order to minimize your efforts and the time you spend on this. So what you can do is that instead of finding that 5th position for every single duration, just visually have a look on the box plots of the values and see where the peak basically is going to happen roughly. So you can shortlist a few durations that potentially can give you the highest 5th position compared to the other duration. So let's do that here. If I for example, go all the way down to the 1% even. Let's say my target is a 1% AEP. So it starts from this row 1442. So I select the first duration, which is 10 minutes here, Control Shift downward. I select the whole column for that value. I go up. I still keep the control button, click on this, Control Shift again. So I have the two columns of the flow and the duration selected. Then I go to the insert. I go to this type, which is the insert statistics chart, and select the box and whisker. So as you can see, for different durations on the 1% AEP, which is what I've selected, you can see that the box plot of those 10 temporal patterns look like this. It goes up and then falls down again. So the peak is estimated to happen, or let's say the highest position of the median that I'm looking for is going to be somewhere between 45 minutes to perhaps 1.5 or maybe 2 hours. So that's the short-listed durations that potentially I want to do the manual investigation rather than doing it for the whole set of durations. The manual process takes time, and even small mistakes can slip in. So let's switch to automation for quicker, cleaner, and more reliable results. So if I want to do it a bit faster and perhaps more systematic, I can use the formulas available in Excel itself to automate the process and get the results for the whole set of data at once. So imagine this is my favorite output that I'm looking for. So I want to have the 5th position flows for each set of 10 values of flow that I have for every single duration AEP case. I want to also have the record of the row number so I can later go and check the values if I want. And of course the duration, the AEP and the TP associated with that specific selected 5th position. So basically that will be the output that I'm interested in. If you scroll down here, you will see that in total we have 1680 rows, and that means that here my output should be 168 because we have 10 temporal patterns. We just choose. I do the whole process at once, means that I run it for all the AEPs at the same time, but as I said earlier, we only look into specific AEPs when we want to select our critical storm duration. I first go to cell F, and this is the formula that I have drafted. So it uses the large function. Basically it is looking at the 5th position of the values, and it is setting it at cell F2 in order to get the 5th position of the first row of the value. Then after that, I paste another formula that I have created here. As you can see, this one basically uses the match function. It goes and finds the value of, let's say, 0.617 and identifies what is the row number associated to that. After that, the job is easy. I'm going to basically check the index associated to the duration column A, which is corresponding to the 5th position that is selected. And I'm going to repeat that for the AEP and TP as well. Once done, I just select all the values and drag it down to the cell 169 because we have the header also. So you see that by this method, I can just find all the values that I want. So let's say if I'm interested in 1% AEP, I just need to look into the values that have 1%. So basically these are the desired values for me. I just give them a yellow color first. So what we need to do is basically look at the column of the flow, which means this column, and see what is the maximum number that we have got. If you remember when we plotted, the visual investigation showed us that we are going to have a bell shape. So it means that the peaks or the 5th positions are first going up and then coming down. So as you can see, they start from 11 all the way, go hit the peak of 33, and then after that gradually goes down. So 33 is the highest number that I get, and that will be my desired value. So this is what I'm going to choose. So the answer to the question is, for the 1% AEP, the critical storm duration is 1 hour event, and the peak flow is 33.115 cubic meter per second. And you can do the same process for any desired AEP. Excel is great for automation, but what if we could take it even further? With Python, we can streamline the entire workflow, eliminate manual effort, and generate results instantly. Let's dive in and see how powerful a few lines of code can be. The Python code that I've written uses the pandas library, external library for the data handling part, and it has 118 lines. It's not a big code, and it is supposed to do the same process that we did last time with the Excel formula. So I just close my code. So this is the new Excel 5 that I created. So basically the code is supposed to fill the columns similar to what we did last time. So I close this one, and then after that I go to the command prompt that we can use the Python codes there. So I type Python and then the name of the code that I've written and press enter. So it starts to run the code, and that fast I get the results. So now let's have a look on the outcome and just compare it with what we got from the Excel. So I have put the two results beside each other. So I go all the way down to the 1%. So I just do the same thing, but this time I give it a different color, like for example blue, and then I compare the values. You can see they are exactly same numbers, but much faster are produced by the Python code, and again same peak under the same duration is selected. So basically they are doing the same thing, and of course the Python code is much faster. So as you've seen, finding the critical design storm in RORB can be slow and tedious when done manually. That's why we built automated solutions in Excel and Python, making the process faster and more reliable. Identifying the critical design storm is a big step in drainage design, but it's just one piece of the puzzle. In the next video, we will dive into flow routing to see how the flood waves move downstream, transform in shape, and affect different points across the catchment. Stay tuned, you won't want to miss it.